Diego I invite the Professor Diego for introduce our Professor Karl Kunisch for next talk.
Okay, thank you very much, Mauro. So for me, it's a great pleasure to introduce Professor Karl Kunisch from University of Graz in Austria. Professor Kunisch is a full professor. Now he's retired, but he was full professor in the University of Graz in Austria. And he made many contributions in the optimal control and numerical analysis as well. And Professor Kunisch is authored over 360 publications in peer-reviewed journals, and he has more than 6,000 of citation in MathSciNet. Yes, he's the numbers of Professor Kunisch is really impressive. His age index is over 49. So it's a great pleasure to have you here in our seminar. And Professor Kunisch is going to talk today about learning-based optimal feedback control of nonlinear differential equations. So, Professor, the word is yours.
Thank you very much, Diego. Actually, I should maybe start by saying that I had the big pleasure of having Professor Diego de Souza as a, if I may say so, postdoctoral student several, I don't know, maybe 10 years ago or something, when he was one of the group members of my ERC grant, and he really contributed a lot to some aspects of controllability of systems of differential equations, the monodomain equation, in fact. Before I start, let me just make sure whether I'm well understood. Can you hear me well?
Yes.
Thank you. All right. So I have the pleasure to still work at the University of Graz and also at the Radon Institute, which is an institute for applied mathematics sponsored by the Austrian Academy of Sciences. I am going to talk on a topic which is maybe not so familiar to some of you. So I take the liberty to really start, to at least try to start, quite slowly. So to explain the problem, to explain why there are challenges, and then to explain my contribution, our contribution. So we are talking about dynamical systems which are nonlinear. At the moment, it's not so important if we have in mind an ordinary or a partial differential equation. What's really important that we allow a control, an external, if you wish, force to act on the system. And the force should be chosen in such a manner that some cost functional is minimized. In this case, I choose an infinite horizon control functional. So I minimize over some set of U of admissible controls the running cost involving the state and a penalty, a cost on the control. One of the most important optimal control problems are stabilization problems. In this case, f at 0 is 0. Many times the running cost is quadratic. And the name of the game is to choose U in such a way that the trajectory is steered to 0 from some initial condition by 0. So stabilization. So as such, for the moment, you may look at it as just an optimization problem. You minimize some functional depending on two variables, y and u, and there's a nonlinear equation as a constraint. Okay. And if you're an expert in minimization and have many codes available, then you discretize this problem and simply solve the optimization problem. And at the end, you have a good U, and that's it. If you prefer to look at the differential equation as a constraint, you can look at the differential, you can introduce an equality constraint. Now you have two variables, y and u, and you're solving this constraint problem. And over the last 20, 30 years or more, many contributions have been made to solve such optimization problems where PDEs or ODEs arise as constraint in an efficient manner. I refer to them as open loop control problems, which is to say, as an example, if I was to try to go from Frankfurt tomorrow to Brazil, okay, and I compute my optimal trajectory, my best control to fly, and tomorrow morning I utilize it, okay, it may work excellently, but maybe the weather has changed. Maybe some other problem arises. So my state, so there will be perturbations to the system, but now I cannot act on that. I would have to start all over again. So that's the disadvantage of open loop control. In open loop control, you have a dynamical system which depends on a control. You have a control input, you optimize, and then you go. And whatever you did, it's going to happen. Very differently in closed loop control. You look at the dynamical system, you observe the state, maybe with some observation operator. I'm not going to talk about observation today. And you would like, and you characterize your optimal control by a feedback. So you look at the state, and the optimal control is a function of the state. Okay. So what we have now is, first thing is you just have a control, or you have an optimal open loop control, or you have a feedback. You look at the state y, and depending on where you are, you control. Depending on how the temperature is, you turn on more heat, or you turn on the air conditioning, or you do this in an optimal way. What we want to do today is to find the feedback operator in an optimal manner. All right. And let me start first with the linear quadratic case, which is to say the dynamical system now is a linear one. You may think of simply a matrix or Laplacian for the heat equation, or the linear or the Stokes operator. You have a control and you minimize the cost. Under some well-known assumptions, namely detectability and stabilizability of the operator A, I will not go into that. The following equation, the following algebraic Riccati equation, involving the state operator A, the control operator B, possibly some operator involving the state in the running cost, D. Under reasonable assumptions, there exists a solution pi to this nonlinear equation, to this Riccati equation. All right. The operator pi, if A is a square matrix, then the pi is an n cross n matrix. Otherwise, it's an operator in the Hilbert space or in which A is operating. Once you have pi, if you are able to solve this Riccati equation, then you may do the following operation. You let pi act on the state, followed by B transpose, or B star if you're in Hilbert space, adjoint operator. You determine this to be your control, and that's in fact, and that's a well-known result in linear quadratic optimal control. That's the optimal control in feedback form. It's in feedback form because it tells you what your control at time t should do, depending on where your state is. Okay, and then we can take this control, stick it into the system, and that's what's called closing the loop. And then you have a closed loop form for the optimal control, and you just run along this optimally control trajectory. Of course, even now let's think towards nonlinear problems. Since we have such a fantastic theory for linear quadratic problems, why don't we try to use it in the nonlinear context, which is to say, we linearize around the trajectory, and then we are carrying out this procedure for the linearized problem. Of course, we have to, in this case, think of time-dependent operators. This linearization works very well in practice. It works very well locally in the neighborhood of the linearization. And many people have worked hard on justifying this linearization approach. Now let's do a step towards the nonlinear problem. All right. This is the nonlinear optimization problem, and I would like to make a step towards solving it. To do so, I have to introduce what's called optimal value function, which at first sight may be a function which is not so clearly well motivated. But anyway, what does it do? You look at this problem as a function of the initial condition. For every x, for every initial state, you consider the optimal value of this optimization problem. Of course, it depends on x, it depends on u. And this function, this optimal value function, satisfies the so-called Hamilton-Jacobi-Bellman equation. Okay, this equation, where at first it's even difficult to read as an equation, because before we can consider the left-hand side, we have to even carry out the minimization problem. So we have to minimize over u, then everything is a function of x. And then this equation here is the HGB equation. Okay. It has a boundary condition. If we start x is equal to 0, then of course, then we are at the origin. F is 0 is 0, L at 0 is 0. So let's just take u equal to 0. So f at 0 is clearly 0. And a little bit of thinking, the gradient at the origin is also 0. But of course, now towards solving. In general, solutions, if they exist, are not C1. Rather, they allow only what's called viscosity solutions, which were investigated or introduced, among others, by Pierre-Louis Lyons and Grendel. A Fields medal was dedicated really to Pierre-Louis Lyons in the solution process of HGB equations. For today, I'll assume that we are in the C1 world. I don't worry about the lack of differentiability. Let us observe that if the set of controls is unconstrained, it's just the whole space, then this minimization with respect to u is quadratic, and we can do it by hand. And u star is equal to this formula here, we just calculated. So we have the optimal control also in the nonlinear context, provided we know v. If we would know the minimal value function, then we had conjunctive, then we had the optimal control. And again, we can close the loop. Before I did it with the Riccati solution, now I do it with the gradient of the value function. I close the loop. So if I can solve the HGB equation, Hamilton-Jacobi-Bellman equation, then I have my problem solved. But it's not simple, and the most obvious, the first difficulty that arises, it is that this, even after the simplification, is a nonlinear hyperbolic, first order hyperbolic equation in the unknown v, depending on the variable x, and x is the state space variable of the dynamical system. All right, this x is this x, which is the space. So the dimension of this first order nonlinear hyperbolic equation is that of the state space. So if the ODE is in dimension 5, this is a hyperbolic equation in equation 5. If this is the formal writing of a PDE, a nonlinear PDE, that's a hyperbolic operator valued hyperbolic equation. So this is the challenge. And this is referred to, and this has been recognized in the ODE world for many, many years. And it's referred to as the curse of dimensionality of solving Hamilton-Jacobi-Bellman equations. All right. Bellman in the 60s, at the origin of dynamical programming, wrote what cast the pall over our victory. The curse of dimensionality, a malediction that has plagued the scientists from the earliest days. Well, I have read about the Vita of Bellman, and he was a very, let me say, lively and colorful man. So maybe he exaggerated a little bit. I don't know what he meant by earliest days, but anyway, it was clear that this is a challenging problem. So if you think of discretizing this equation, this PDE, in each dimension with, say, finite difference or finite elements, and you use a grid of n nodes, and if the state spaces are D, then this has exponential complexity with respect to the dimension. So this, and how to solve it, that's really a challenge. So now, the question, and I wanted to make a contribution towards solving it. And then, of course, the question which was at the beginning was always in my neck was, is it worth the effort? Okay, because Riccati equation does such a good job, and in many cases, and it has been used and is being used in the engineering literature all the time. So are there situations, serious situations, where HGB solving would really provide solutions where Riccati fails? A posteriori, that's sort of simple, but when we started doing this, working on this topic, numerics was challenging in this context. So yes, for sure, we could solve now, and we can say, yes, it's worth the effort. So what today I will talk about one aspect, which is training neural networks to solve it. But before I continue and explain what we suggest, let me just give a sort of a summary of the techniques which I am aware of to start solving HGB equations. of course, you can open the literature, what the specialists on numerical analysis have to say, right? And they're excellent codes. But I think it is fair saying that after dimension 3, 4, 5, the classical techniques fail. Then they fail. Next one is interpolation from open loop data. So what do I mean? You solve the optimization problem, the open loop problem, for many initial data. So, and then you have this cloud of data, which you interpolate to the best you can. When I first heard about that, I thought that's sort of a little bit naive, just interpolation, right? So yes, we can all do that. And would it be powerful? I quote some people, and then we have contributed also. And in fact, this is a very, very powerful technique. From an engineering point of view, that's really I can suggest. Then one technique which can be used is you look at the hyperbolic equation here. It's nonlinear. Okay. You do a Newton step and you solve the Newton step. And if one combines this with tensor calculus, so you need to still discretize. Of course, we don't do this with finite elements, finite design. We do it some globally defined ansatz functions, and then combine it with tensor calculus. That's a very powerful technique as well. One can do Taylor expansion. There are Hopf formulas. The Hopf formulas, I should mention for the sake of completeness, but I think they are not very general. One has to have very specific problems to make them applicable. There are max plus algebra techniques, which I am not an expert in, newly developed now tree structures. All right. Now let's go towards training neural networks. All right. Towards training neural networks-based feedback. I allow myself to repeat the problem under consideration. This is this one. And if we state some theorems that I would like to state them in the space W infinity, which is the set of all now I really take I take ordinary differential equations. So W infinity is the space of all L2 functions whose derivative is L2. B is an n cross m matrix, so it's an m-dimensional control. B maps from Rm into the state space Rn. F is a nonlinear mapping. F at 0 is 0. Our interest is, of course, optimal feedback stabilization, and y0 will be in a compact neighborhood y0, capital Y0 of the origin. And everything, and I assume that for all these initial data, this infinite horizon problem has a solution, which means I assume stabilizability in a neighborhood of the origin. And henceforth, I work in this neighborhood. All right. Now, the learning ansatz is the following one. I'm looking for a feedback operator. I'm looking for an operator F which acts on the state and provides me with the control. In the linear quadratic world, this was the solution to the Riccati equation. In the HGB world, this was the gradient of the value function, which I say I cannot go for it directly. So somehow I avoid the difficulty for a while. Okay, I say I'm looking for an operator F in some space of Lipschitzian functions. with the property that f of 0 is 0. That's what we know. And this f is of course is the candidate for the control. So wherever there was a u before, I write f of y now. U square is now f of y square, f of y. Okay. So I say I want to minimize over the space of all functions f. I have space of all functions f. This optimization problem. I call it the learning problem. Okay, well, admittedly, this is now, learning is now a buzzword in a certain sense, but it is useful, right? I could also, because I want to train, I want to learn the feedback map. Okay, I was not specific about the space now. Suffice it to say, or to make the following comment, right? I am trying to find a function from a high dimensional space into the control space, but the piece of information I have is only basically the trajectory from one initial condition. So if you think of the heat equation, its trajectory is not very interesting. It just slowly goes to 0. If you think of the wave equation, well, if it's unnamed, then you just have an oscillator. You don't see so much, right? You just observe it, basically a circle in Hilbert space. Or if it's an oscillator, you just observe a circle in R2. So it's maybe hopeless to find this function, right? So the next, then you can say, yes, it's not only from one initial condition. By the Bellman principle, you can replace this y0 by every yt. You can use the Bellman principle. Yes, I learn along the whole trajectory. I'm learning. Yeah, but no. That's still not enough. So now what we say is, let us take an ensemble of initial conditions. Y0, I is from some finite set for the time being. And for all these initial conditions, I solve this optimization problem and then I average over my cost. Always subject to the dynamical system y0 at y0. So it's very important that I am slow at this moment, because this is the formulation of the learning approach for getting F. All right. We want to be a little bit more fancy, bringing in some measure theory. I now take a measure space, a complete probability space, y0, this is neighborhood of the initial condition. I endow it with a sigma algebra and a measure, and I do this learning with respect to these measures. Okay. Well, the first thing is that one can check that this problem admits at least a solution in this, and that it is pointwise equivalent to almost everywhere sense for each specific initial condition. So far, so good. All right. Now, with an eye towards implementation, what to do? I haven't specified H yet, okay? So all these functions, somehow we need to parameterize these functions. Okay, at the beginning, I mean, we have all the choices available, right? Except for finite differences and finite elements, because it's high dimensional. And then, no, it cannot be a grid-based. It shouldn't be a grid-based approach. It should not be a grid-based approach. Now, since we are somehow have chosen to be living in the times of neural networks, why don't we try neural networks? Okay. Okay, so some of you are maybe experts in neural networks, but at the beginning, I did not really know what a neural network is. So let me take one slide to just explain the key ingredients of the neural network discretization. So at this moment, I leave the optimization aside. I have one slide on neural networks. Basically, a neural network, follow my mouse, please. A neural network is the superposition of simple functions, simple in the colloquial sense, simple in the sense that each function is affine with a rectangular matrix Wi acting X and an offset Bi. Okay, so the Wi and the Bi are the parametrization each one of them. And this is going to act, the image of this is some Rni minus 1 or Rni. And then there's a sigma, what's called activation function, which is symbolically now written here, but what it means, it acts on each one of the coordinates. It acts coordinate-wise. All right. So each of these elements of this superposition operation is such an affine followed by an activation function, except for the uppermost level, which is just an affine map. Such, okay, the parameters, theta, are the matrices and the offsets, Wi's and Bi's. And we remember, then we have to take care of the dimensions. All right. So we are discretizing like this. Of course, our X in this case is our state space. All right. And then if you read, or when I read the literature on the neural networks, of course, there's one literature on which would tell us something about how they, about approximation properties or rate of convergences. The other literature tells us how they can be used in practice. And in practice, many times the authors stress the fact, use all the information that you know about your problem in setting up the network. Well, I didn't really know how I would use information. Number one, I didn't know from the optimization what is the relevant information. Number two, then how to put it in these matrices. But if you remember, I said that the value function at the origin is 0. The value at the origin. So let's do that for our feedback mapping, okay? For our feedback mapping, now depending on the parameter theta, at x equals 0, it should be 0. So at x equals, so I simply subtract that. It looks sort of it looks completely trivial at the moment, but if we do not do this in our numerics, simply we had no chance. All right. So much on a recapitulation of neural networks. All right. Now, before we show numerics, let's provide at least one theorem, which is simply about approximation. Now I looked at the literature on approximation. This was about maybe 2 years ago. And then you can see a lot on the approximation in the topology of C, in the continuous function, supremum topology. But okay, we definitely need also the gradients, because the gradients are going to be our controls, the derivatives. All right. We did not find what we needed to in the literature on neural networks concerning derivatives. Moreover, from the point of view of numerical implementation of these optimization problems, we would like maybe constraints on the parameters. The parameters, remember, are the matrices from these affine functions. So what is known, or what can we prove about neural network approximation in the C1 topology in the presence of constraints? Well, at that moment, we couldn't put constraints on everything, but at least in the lowest, all the offsets we could constrain, and the lowest layer we could constrain. Then, given any epsilon, there exists an architecture, there exists a number for the layers, and such that a neural network with neural network parameters approximates to epsilon accuracy in C1. All right. Then, once we had that, then of course we are going to we use that architecture to in our situation for to approximate the feedback function. So the next thing is, can we also approximate the trajectories by the control trajectories by replacing the control by a feedback? And yes, this can be done with the same level of accuracy. And then what do we do next? Now, what used to be the H that I haven't been talking about yet, this is the architecture from the neural network. Okay. Now we replace our feedback mappings by neural network architecture. These are the parameters. Okay, it says that my internet is weak, but I see that Mr. Sousa is still not complaining.
That's okay. That's okay, Professor.
Okay, so it's good. And then we have some, okay, we have some penalty on some of the parameters. I do not go into that. There exists global minimizers, and we have convergence of the costs, and we have at least every weak accumulation point of which there exists at least one is a strong accumulation point. So we started the approximation by neural networks. So far, so good. Now comes numerical realization, the first step in this direction. Of course, all the now I step towards what did we do in practice. Of course, we had to solve the open loop problems. Why did we have to solve the open loop? We had to be able to compare. So we solved it for T sufficiently large. Okay, we always fixed the layer size 8. Now I would do smaller layer sizes, but at that time we did that. Now these activation functions, which I said, remember I said they act component-wise. There is something which is very frequently used, are called the max function, max of 0 and x. But we just regularized at the origin. All right. But max of 0 and ReLU function, it's called ReLU function, which is one of the most frequently used activation functions. Then from practical importance, thanks goodness, somebody suggested this to us. There are residual connections. That was very good in practice. And then we started to implement. Of course, the first implementation we did was for a linear quadratic problem. Because, why? Because there we can compare with the Riccati solution. And if we fail there, then it's no use to continue. But we were lucky enough to that the electrical networks that we tested, linear quadratic cost, it worked well. So we went to a Van der Waals-like equation. Van der Waals-like, because we added such a destabilizing nonlinearity. All right. Otherwise, up to here, it's just Van der Waals with a controlled Van der Waals. It's still not high dimensional, but it's worth to test. That's really something where you that's nonlinear, right? There's no Riccati available. So for feedback, you need to do something. And now comes mainly a comparison to the between HTB and Riccati. Let us look at these 4 plots. Number 1, the abscissa and the ordinate are the y1 and the y2 axis of the state. The dots are initial conditions. At the moment, red and blue have no specific meaning. You please simply follow my mouse. We are starting here that as time increases, we are running to this manifold, and then we go to infinity. The origin is not stable. This is true for every blue and for every red dot. All right. So, but this is uncontrolled. So it's no surprise that without control, all the trajectories escape to infinity along these manifolds. Now, we take the linear quadratic regulator problem with the same initial conditions. Okay, the same initial conditions you see in the neighborhood of the origin. Where's the origin? The origin is here. Here's the origin. In the neighborhood of the origin, the linear quadratic feedback, okay, they converge to 0. But if we go too far away, again they escape. All right. And next one is, there's what's called a higher order linear quadratic, higher order Riccati, which the engineers like to use. And then in this case, it stabilizes, but along strange trajectory, the control is extremely expensive for that. And now we go to the neural networks that I propose. And now for the neural networks, we follow again the trajectories, but now we distinguish between blue and red initial conditions. We distinguish between blue initial conditions, which were used to compute the feedback in the learning ansatz. All right. In the learning ansatz, yes, we nicely converge always to the origin, also far outside. So those blue initial conditions were used for the learning approach. But now we use some initial conditions which were not used for the learning approach. So you invent a new initial condition, and let's use the same feedback on them, and they also converge. So neural networks, they did a very nice job in this, but still admittedly low-dimensional problem. And then we went to higher dimensional problems, and again it was quite successful. We solved up to, with discretized PDE, as I will show in the next slide. But before that, I would like to do a paradigmatic change. There's a noise in the background which I have to turn off. Excuse me. So we had the neural network running well. And then I said, or we said in our group, why do we stick to neural networks? Well, there's one clear reason, right? So many people work with neural networks now. So we also tested them. But there are other techniques. There are other possibilities, which are polynomials. So why don't we replace this space H by polynomials, in our case, by polynomials of a special format, monomials. Okay, so the ansatz for the value function is a sum of monomials with parameters theta, as before, okay? what we do is we take them up to order S, but the order S is by, we could take the highest order, we could take the sum, we multiply them, these powers, and up to multiplication up to order, up to product S is in the space. And then we take out those which are in the kernel of the feedback operator. And then we look at the closed loop, but now by polynomials. And we look at the adjoint equation. And then we made numerical work on that. For example, what we see many times, we have to evaluate monomials or the derivatives of such functions. So we use graph theoretic techniques for evaluating the first, the second, also the zero first and second derivatives of the value function. We prove the convergence in the, which is called in this learning environment, it's called generalization. If it's not only for the initial conditions that we train, but in the neighborhood of the initial condition. And we found that currently in our numerical realization, the polynomial-based approximation is in practice more efficient, I would say, than the neural networks. And to give one example before closing, we are looking at an optimal control problem subject to a PDE. Now, it's the Yon-Kahn equation. It has 3 steady states. 0 is a steady state. It has at least 3 zero steady states, maybe more. No, this one has 3 steady states. Yeah. 0, -1, and +1. We control on subsets little omega I of the domain. Our domain was 0, 1. It's one-dimensional. On small subsets, we have controls, which are the amplitudes, UIT, here, with Neumann boundary conditions. Now, this is an infinite dimensional system. We didn't want to talk about HGB equations in infinite dimensions, so we discretized by Chebyshev polynomials of degree 19 here. So eventually we solved the HGB equation of dimension 19. The monomials had hyperbolic cross degree 6. We had a sample size of the domain was -10 to 10 degree 19. This is this 19. We trained our feedback by only 5 initial conditions. All right. And now my time is over. I'm basically finished. Now in the final, after discretization, I should say one word about how we penalized, or the control cost. The control cost is on the parameters theta of the expansion. And we did a combination of L2 and L1. L1 always takes care of sparsity of the controls. So if some parameters are not really large, anyway, L1 makes it immediately 0. And now, okay, here is the result for one specific choice of gamma, and then there's a smaller choice of gamma, which allows it to be better. Sure, this is relatively large. We know it's much too large for a penalty term. And here we compare the optimal value on this axis, which we just computed for the sake of testing, okay, by open loop control. The optimal value compared to the learned objective value. Of course, the best would be on the blue line, because then the learned has the same smaller size than the optimal one. Well, it's a little larger, so it's a little bit to the right. it's a little bit to the right. These are different initial conditions. These are the results from different initial conditions. We had an big array of different initial, and it just works extremely well. If we take a little bit more adequate cost for the gamma for the cost, it works more nicely. Of course, we cannot take 0 and it blows up. So there is always some learning along these lines. So with this, I would like to, I need to realize that my time is over. I thank you very much for your attention. On the slides, you will find a short list of references, and if you are interested in write me a short mail, I can provide you with files. With that, I really appreciate to have had the opportunity to talk in this seminar. I forgot to mention I had looked at the list of speakers of this seminar, and I'm really honored to be one of them. Thank you very much.
Thank you so much, Professor Kunisch, for this wonderful talk. So now we open the turn for questions or comments. So if anyone has some question or comment, please raise your hand or open your microphone. Or you can type your question in the chat.
In the chat, okay. Do I have to open the chat? My chat is not open. Control L. Okay, where is the chat? I don't see the chat. But Diego, you could read the question in the chat to me, maybe.
Yes, I can read, but no one.
At the moment, not.
Yes,
okay,
yes.
I'm sorry if it was
No,
not.
no. Maybe there is some question of by Enrique.
Okay, thank you. Thank you very much for your talk. It was very, very interesting. I have one question. I don't know if you have tried to consider a boundary control problem with the same technique, with the same. Have you tried to apply the search of feedback law with neural networks to a boundary control problem?
No, the answer is now I know what EFC stands for, Enrique Fernandez Karl. Hi. No, I have not. I mean, this of course would be relevant in this Allen-Kahn equation and so on, right? No, we have not yet. No. It would be nice, but we have to do step by step. Okay, so no, not yet. But now I'm getting quite confident. I mean, yes, I think we can start thinking of obtaining approximate solutions for PD-related optimal control problems with boundary control. Yeah, no.
Okay.
We had some bilinear control problems in the Fokker-Planck. That's what we did, but not boundary.
Okay, and second question, I don't know, well, if it is relevant or not, but have you tried to find an estimate of the computational cost, for example, with respect to the parameter that you have gamma? I think that it was gamma or beta. Have you tried to find which is the cost with respect, in order to get something? I mean, close to controllability or to approximate controllability?
That's the question. If I may repeat, I think I hope I understand. I think you are interested what happens as you let beta go tend to 0. right?
Yeah.
Or after parametrization that gamma tend to 0. No. I have not. No, we have not done that. Of course, I understand that you are interested in this because as beta goes to 0, you are getting closer to. You can formulate exact control or approximate controllability problems along these lines. No, the answer is no, and I think this is really challenging because I'm for the neural networks, because even for simpler situations, to estimate the complexity of the neural network in terms of parameters, or to estimate the complexity, is really is some topic which is very, very recent. Very recent. I know that there are papers, but I'm not an expert on that. No. But may I ask back, Enrique, since we is feedback control for exact controllability, is this an issue?
Not for exact, but I think that for approximate controllability should be.
Okay, thank you. Okay, all right. Thank you. So we could work on it.
Thank you very much.
Okay.
Okay, is there any other question, Enrique or anyone? Karl, I have just a curiosity in your learn problem.
Yeah.
You took affine solution, no? Sigma I X and what is yes, I think that is the next slide.
Or the previous slide.
Yes, this one. Yes.
Yeah, I took.
You took at some point you took some functions like sigma I X plus
Yeah.
Why do you took that? Because
okay. No. Now I know you meant this one.
Yes,
the sigma.
Yes, this one. Yes, the neural network. Yes.
Okay.
No, this W.
For the neural networks.
Yes. Why do you took the FE theta something like that?
Okay. No, this
could
is really.
Hmm.
Okay. So you are asking me, why did I take this?
Yes.
That's really the definition of a neural network.
Okay.
So this is like if you were asking in the situation, say, of B-splines, why do you take this? Why do you take this kind of a definition for a B-spline? Well, it has proven to be a good approximation for smooth functions, right? So this is really the definition of a neural network, completely disjoint from the optimal control situation in this case. Yeah? If you approximate some other function by a neural network, this is the definition of neural network. Okay. Of course, the question now arises: which structure is there in the feedback? Why we should maybe which type of activation function sigma? I do not know. Okay, I don't know. But in this neural network literature, this is still there's a tremendous amount of discussion on how to choose sigma. All right.
Okay. And also in the functional that you show during the talk, you have quadratic terms, right?
quadratic term, generally speaking, but then in practice, I added in practice, I added an L1.
Ah, you add L1, and here in this slide you have a finite time horizon, right?
No, in this, yeah, I have a finite horizon, but this is T is
Okay.
okay, yeah, but this was already in the numerical situation. So T is so large.
It's so large. Okay. Okay.
That it's T infinity.
Okay. Okay. Okay.
Yeah, I mean, that's always how do you numerically realize, except if you use specific ansatz functions,
Okay.
Legendre polynomials or something in time. But in practice, T is large. And we tested this before that this was well chosen.
Mm-hmm. And also, do you have three controls there? No, the sum.
We had three controls.
Acting.
Yeah.
And this is because the model or why?
Well, I will.
Or if you increase the number.
No. I think I know that with three controls, I know we can stabilize.
Okay.
I know we can stabilize. Maybe we can stabilize with less, but we have theorems on the stabilization on how big the omega I has to be and so on, and how many you need to know. We had, and I'm sure I took a configuration where I know we can stabilize.
Okay. 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 Thank you. Thank you. Thank you, Professor. Any other question or comments? So it seems not. So let us thanks again, Professor Kunisch, for this wonderful talk. It was a great pleasure to have you here.
Thanks.
Okay, so
I appreciate it.
Okay, thank you. So now Professor Mauro will conclude the section.